In this lesson, we're going to get into some more counting techniques. I'm going to start by looking at n factorial a little more closely. Last video, we saw that n factorial was just a way to write a descending series of multiplication. For example, 8 factorial, 8 times 7 times 6 times 5, all the way down to times 2 times 1. There are a couple of more meanings for this. It can also mean arrange a certain number of objects in a certain order. For example, you have 8 books that you're going to put in some order on a bookshelf. You have 8 choices for the first book, 7 choices for the second book, 6 choices for the third, and so on. You have 8 factorial ways to arrange those books. In this class, there are 12 people. So when I made a seating chart back in January, I had 12 choices for who was going to sit in the first seat, 11 choices for who was going to sit in the second seat, and so on and so on. I was arranging a group of 12 in some order, and that ended up being 12 factorial. There are 12 factorial different seating charts I could have created. There's one more interpretation of n factorial. Choose n objects from a group of n. And again, it implies that we're doing this in some order. So using the book example, I can select 8 books from a group of 8 factorial ways. If I am looking to create some sort of 8-digit number where all the digits are different, I have 8 choices for the first digit, 7 choices for the second digit, and so on. If I have 8 letters, or even, let's say, 12 letters, I choose 12 letters, I put them in a hat, like Scrabble tiles, if you've ever played the game Scrabble. Let's say I choose 12 of those letters, assuming they're all different. There are 12 factorial ways that I can create a string of 12 letters. Those are all interpretations of n factorial. We are selecting every object in a group, selecting 8 objects from a group of 8, 15 objects from a group of 15, and so on and so on. What happens if we don't want to choose everything? I want to choose a number less than n. For example, I don't want to choose all 8 books. Maybe I just want 3 to sort of be highlighted. If I'm a car dealer, I have 500 cars out in the lot. How many of them? I don't want to choose all 500 to put inside the showroom. I want to select maybe 5. How many different ways can I choose 5? If I am, say, a bakery, and I've got all these cakes and cupcakes, I can't put every single one in the little featured display case. I can only choose a few. So say I've got 150 of those, but I can only highlight 4 of them. How many ways can I do that? So there has to be a way to choose a smaller amount from the entire group. My seating chart example, how many people can sit in the front? Back when we actually had class face-to-face, there were 4 people that sat in the front. All 12 people can't sit in the front desks. Only 4 can. So I had to choose 4 out of 12. So how do we do that? How do we choose a number smaller than n? Smaller than the entire whole. Well, let's take a look at that. Here's a group of 5. And it says choose 3. So what I've done is I've chosen 5 smaller groups of 3. So I have these A, B, C, D, E are my 5 things. Here are groups of 3. These are not all the possible groups. But here's 5 groups of 3. One big question that we have to answer, looking at the 5 groups, ABC, CEA, DEA, DAC, CAD. These 2 groups have the same members. And the big question is, are they the same? Are they the same? If yes, then we've really only chosen 4 groups because we can't count the same group twice. If these are the same, I only have 4 groups. 1, 2, 3, 4. If they are different groups, then I have 5. So that's one of the big questions we have to be able to answer. Is shuffling the same members around creating a new group, or is it not creating a new group? And sometimes the answer will be yes. Sometimes the answer will be no. Let's say that when I'm choosing these 3 people, let's say these are first letters of first names. Let's say the first person chosen wins $500,000. The second person chosen wins $50,000. The third person chosen wins a 3 Musketeers candy bar. It does matter who is chosen first over here. D is chosen first in this group, $500,000 winner. D is chosen last in this group, just won a candy bar. There is a big difference between 500 grand and a candy bar. So in that situation, we have 5 groups because the order that people were chosen in mattered. Here's another situation. Same thing. These 3 people will all win prizes. But each prize is $1,000. Chosen first, you win 1,000. Chosen second, you win 1,000. Chosen third, you win 1,000. Now it does not matter who is chosen first, second, or third because all the prizes are equal. So what we now have are 4 groups. This is a repeat. It's nothing new. So we count both of these as just 1, 2, 3, 4. Those are the 2 situations that arise. And the terms we have for them are permutation and a combination. A permutation, order matters. Combination, order does not matter. In a permutation, we have 5 groups. In a combination, there are 4 groups here because this repeat is irrelevant. It did not change anything. With a permutation, the order things are chosen is important. This is a different group than this, even though they're the same 3 people. A permutation would be the example 500,000, 50,000 candy bar. A combination every position is treated equally. Changing the order does not change anything else. So under a combination, these two groups would only count one. Under a permutation, they each count separately. You've probably seen permutation and combination before if you've been messing around with your calculator. Permutation looks like this. We have a lower little n, little r, and then a p. We just pronounce this nPr. Combination looks like this, nCr. And what this means, the n is the size of the group. R is what we are selecting. We have a group of 5 people. I want 3 winners. I have 12 students. I want 4 people to occupy the front desks. We have 20 people in a group. I want 3 leaders, and so on and so on. So here's how we calculate these. Both are very similar. nPr starts out with n factorial. But then we have to divide some things out. We divide out the things we don't want. For example, I'll go back to the group of 5, select 3 winners. I want 5 people to win. I have a group of 5. I want 3 winners. 3 winners. That means 2 people are not going to win. So what I end up with is 5 factorial, divide out the 2 people that don't win, and it ends up being 5 times 4 times 3. It looks like the start of a factorial, but it stops. Because we have 5 ways to pick the first winner, 4 ways to pick the second winner, 3 ways to pick the third winner. There are 120 possible groups of 3 where the order matters. So if I were to go back here and write out all possibilities, I would need 120 groups of 3. And again, these each count separately because they're different. The first prize was different than the second prize. So these are 2 different groups under a permutation. With a combination, it is almost identical. The formulas look almost exactly the same. There's 1 extra. We put r factorial in the denominator to divide out all the repeats. So, back to the winner example here. We end up getting 5 factorial divided by 3 factorial, 2 factorial. Now, what's going to happen here is we still get our 120 from these 2 values, but then we divide by 3 factorial. Here's why. Whoa, I didn't want to do that. Here's why. There are, let's say these are the 3 winners. I have 3 ways the 3 people can be arranged in this spot. two ways they can be arranged, and then one person left. So there are 3 factorial ways to group the same 3 people. In other words, let me go back here. Let me look at this group DAC. I can arrange this group 6 ways. The same 3 people can be arranged 6 different ways. That's 3 factorial. For these 3 letters, I have 3 choices for the first spot, 2 choices for the second spot, 1 choice for the third spot. The same 3 letters can be arranged 3 factorial ways. So this divides out all the repeats of the same 3 winners. Because in a combination, repeats are not allowed. Just shuffling the order of the same letters does not increase our count, because a combination deals with unique groups. All the prizes were the same, so it does not matter who was chosen first, second, third. We have to divide out all the repeats, and that's going to lead to a much smaller number. In this case, we end up getting 60. 5 factorial over 2 factorial was 120. We divide by 3 factorial, which is, that's wrong. We divide by 3 factorial, which is 6. 120 divided by 6 gives us 20, not 60. There are 20 ways to pick 3 winners, 20 groups of 3 winners where all the groups are unique and not just rearranged. On your calculator, we can do nPr, nCr. I'll check my answers here, 5, and then I push math. Arrow over to probability, and here's our nPr, nCr. I will do nPr first. Notice I had to do the 5 first. 5, sometimes we just say 5p3, and we got 60. Because I can't multiply, apparently. That's 60. And that's 10. Wow. And some wonderful multiplication today in my head here. Yikes. Let's try that again. 5 times 4 times 3 is 60. If you've been screaming at the screen for the last 5 minutes that I made a mistake, okay, I just caught it. Divide this by 6, and we should get 10. Better check that, the way this day has been going. 5, go back to math, arrow over, 3. Okay, now all is right in the world. That's how we calculate nPr and nCr. There are a few special values to take a look at. NP1, I have n objects. I want one of them. I have n ways to do that. 10 objects, choose one. Well, obviously that's going to be 10. NPN, choose everything in order. That's just n factorial. nC1. Still n, because we're only choosing one object. If I have 10 objects, choose one of them, I have 10 choices. nCn. How many ways can we choose everything if order doesn't matter? There's only one way. Because every single other way is the same objects shuffled around. That's not a new group. nCn is equal to 1. Now, I promised earlier to explain this. Why 0 factorial is equal to 1. It has to do with this. nCn is equal to 1. That's one of the big reasons. I'm going to apply the formula to nCn. It says n factorial divided by r. R in this case is n again. And then n minus n factorial. So what happens here, these cancel. You get 1 over 0 factorial. And we know the answer has to be 1. The only way this works is if 0 factorial is equal to 1 itself. This was strictly invention. 0 factorial equaling 1, strictly invention. We know that nCn has to be 1. The only way to make it come out to be 1 is if 0 factorial itself is 1. Strictly invention. Time to look at some examples. Here we have another prize situation. 17 people eligible to win one of 3 different prizes. How many ways can 3 winners be chosen? 3 prizes to pass out. One of the things you need to be able to do to solve these problems is answer the question, does order matter? Put yourself into that situation. You are one of the people winning a prize. If you win the first prize, is that different than somebody winning the second prize? Or if somebody wins the first prize and you win the second prize, are they the same or are they different? That's how you determine if order matters. Here the key word is different. The first prize is not the same as the first. So it matters who's chosen first, second, third. This is nPr. 17P3. The way that I always remembered nPr versus nCr, I remembered the word priority. Priority and permutation both start with the same letter. Priority, important. It's important to be at the beginning if something is a priority. Order matters, permutation. The way that I remembered combination, order doesn't matter. We don't care. Don't care, combination. That worked for me. Maybe it works for you too. 17P3. 17P3. there are 4,080 ways to pass out these 3 prizes. Next problem. We have 17 employees work for a particular company, or in a particular company, 17 employees are eligible to receive a $1,000 bonus, but only 3 of them are going to be chosen, and we assume they are chosen at random. How many ways can the winners be chosen? Again, put yourself in this situation. What happens if you're the first person chosen? What happens if you're the second person chosen? What happens if you're the third person chosen? If you are treated the same in all 3 spots, it is a combination. If something different happens, it's a permutation. The key here, everyone gets this. Everyone gets $1,000. Nothing different happens from one to the next. So this is a combination (17C3) (680) for this one. Notice I had the same values in each problem, 17 and 3. Combinations will always be much smaller than permutations because we are dividing out all of the repeats that occur. This will be our last problem for this section. Have a 4-person leadership team going to be created from a group of 12, 3 girls and 9 boys. Kind of sounds like the makeup of this class. Probably a coincidence. How many ways for each of these situations? We're going to choose, for our little pre-calculus class here, a group of 4 leaders. We're going to choose a president first, then a VP, etc., etc. Does order matter? Yes. The first person chosen gets to be the president. The second person chosen gets to be the vice president. The third person gets to be whatever the next position is. Official donut getter or something. The fourth person chosen will be the person that, I don't know, gets all my jokes or gets to laugh at all the jokes, something like that. Order matters. I know that last position, very prestigious one. So is the third one. Order matters. Permutation. 12 P4. $11,880 for this one. I'm going to switch to my other calculator that's off screen. Make this go a little faster. Choose 4 people. Now we're just going to choose 4 people. Nothing that says one position is more important than the other. Nothing that says the first position is special, the second position is special. It just says choose 4 people. Now we have a combination, 12C4. I just want 4 people to be a little leadership team. So we go from almost 12,000 possibilities to 495. Here's where it gets a little tricky, at least at first glance. Choose 4 people. And those 4 people are 2 boys followed by 2 girls. That's where those numbers are going to come in handy. There are 3 girls in this class. There are 9 boys in this class. I want 2 of each. So, nothing that says order matters. Nothing that says order matters. Doesn't matter who's chosen first, second in each group. I just want 2 of each. So, of the 9 boys, choose 2. At the same time, we're going to multiply because it's happening at the same time. At the same time, there are 3 girls. Choose 2. So here we have a product of combinations. I'll go back to this calculator so you can see what that looks like. 9C2. And as soon as I push multiply, the TI understands that this is one calculation, so you don't need parentheses. It treats this as if parentheses are already around it, so you don't need to put any yourself. It understands what's happening. 3C2. And again, your calculator will not read this as 2 times 3. It knows this is nCr, treat it separate. nCr again, treat that separate. And then multiply the 2 answers. We get 108 possibilities. One more problem to look at with this data set. Choose 4 people. Now it says at least 2 have to be girls. So let's look at our possibilities. We could have 2 boys, 2 girls. We could have 1 boy, 3 girls. Or we could have 0 boys, 4 girls. Or can we? There's only 3 girls in this class. That last one is not possible. So we have 2 sets of possibilities. We already know what this one is because we just did it. This one we need to figure out. Well, this is 9C1 times 3C3. 9C1, nC1 is just n, so 9C1 would just be 9. 3C3, NCN is just 1. There's only one way to have all 3 be chosen. So then putting this together, I have 108 possibilities here, plus 9 more possibilities there. There are 117 possibles total. That is nCr and nPr. Make sure you look at the completion quiz and get that submitted. And that is all for this one.